Good morning, guys. Today we will solve some examples related to your temperature. Okay, in previous lecture, actually we have discussed the concept of temperature stresses, how to solve the temperature stresses problem by using our finite element procedure. Okay, so in previous lecture, already we have discussed what is the formulas to find out the load vectors due to the temperature effect, as well as how to construct a global force vector due to this temperature effect as well as due to this point. Okay, so I will just revise all these formulas, and we will solve one example related based on this temperature effect. Okay, so actually in previous lecture we have discussed these formulas, like how to find out the temperature stresses, means how to find out first the nodal forces, what will be the effect of temperature stresses on the nodal forces. Okay, so in previous lecture we have discussed the force vector due to temperature effect. Okay, and what is that? For if this is the element, if we consider this as one element, then for this element, this force vector or nodal force vector due to this temperature effect is given by this formula F1t F2t, which is nothing but equal to minus E1 A1 alpha 1 delta t plus E1 A1 alpha 1 delta. Okay, this is the force vector due to the temperature effect. Suppose a point load is acting at this second node of 400 kN, then the force vector due to this point load will become F1p F2p. At node 1 there is no force acting at node 1, so it will become equal to 0, and at second node the 400 kN is acting at second node, so it will become 400 into 10 raised to power newtons. Okay, and how to construct the global force vector, means by adding these two forces you will get the global force vector. Okay, and by using this global force vector we will construct our force and displacement relationship. Okay, so in this way we can proceed to solve the one-dimensional bar elements, including the temperature effects. Okay, now we will and similarly also we have derived one formula to find out the stresses due to the temperature effect. Okay, and what was that? The formula was, if this is the sigma 1, if we are asked to find out the stresses in this element, then sigma 1 will become similar to previous case, means E1 by 5 in bracket U2 minus U1, and one term is added here, minus E1 alpha 1 delta. Okay, you need to just subtract this E alpha delta t from this previous method. Okay, as already we have derived this term in our previous lectures, you just need to subtract this term E alpha delta t from this previous one. Okay, so this is the formula to find out the stress value. And next is what? How to find out the reactions. The same procedure, means by using the reaction force equations you will get the reactions values. Okay, so in this way the temperature, we need to include the temperature effect by including the force vector into the temperature effect, as well as by subtracting this term you will get the stress value. Okay, now we will solve one example related to your temperature effect. Okay, so we will see one example here. Okay, so in this example there are two bar elements. First one is of aluminium material and second one is of steel material. With all the values are given. For aluminium, A1 is equal to 2400 mm square. Then length for this is 300 mm. Second length is 400 mm. Okay, the next E1 for first aluminium, it is given equal to 0.7 into 10 raised to power 5 Newton per mm square. Next one is alpha 1. For this case, alpha 1 is given, it is a given coefficient of thermal expansion, and it is given equal to 22 into 10 raised to power 6 per degree Celsius. Then for this element, means for steel material, A2 is given equal to 1200 mm square. Then E2 is given equal to 2 into 10 raised to power 5 Newton per mm square, and alpha 2 is given equal to 12 into 10 raised to power minus 6 per degree Celsius for this second element. Okay, all the data is given, and the problem is what? Determine the nodal displacement at node 2, stresses in each element, and the support reactions in the bar shown in figure due to the applied force P is equal to 400 kN at node 2, means a force of 400 kN is given at node 2. A force of 400 kN is given at node 2, and actually in the example it is asked to find out the nodal displacement at node 2. This is node 1, this is node 2, and this is node find out the nodal displacement at node 2. Then also find out the stresses in each element, stresses in aluminium bar as well as stress in steel bar. And next is what? Find out the support reactions, means at left side as well as at right hand side, because these two ends are fixed one. Okay, so these are the terms. Means first find out U2, then next is find out sigma 1 and sigma 2, and finally reactions R1 for this R1 and for this case R1. Okay, and we given that due to the applied force P is equal to 400 kN and temperature rise of 30 degrees Celsius. Okay, here they have mentioned that the temperature rise of 30 degrees Celsius means what? They have given the value of delta T is equal to 30 degrees Celsius. Temperature rise what means it is the difference between surrounding temperature and this material temperature. Okay, so the delta T or temperature rise is given equal to 30 degrees Celsius. Also they have mentioned the coefficient of thermal expansion is alpha 1 for this aluminium as well as for this steel. All the values are given. For A1 is for this material, A1, E1, alpha 1 is given for this material, A2, E2, alpha 2 is also given. Also length for this aluminium as well as steel is given 300 mm and 400 mm. Okay, and here we need to find out the first displacement, second stresses, third one is reactions, and this example is asked for 12 marks in your end semester examination. Okay. This is asked for 12 marks, means each term for 4 marks. Okay, now we will try to solve this example. Okay, so temperature rise of 30 degrees Celsius is given. Delta T is equal to 30 degrees Celsius here. Given that delta T is equal to 30 degrees Celsius. Okay, now find out the first displacement, nodal displacement at node due to this temperature effect of 30 degrees Celsius. So, first step is what? Same procedure. We will apply our same procedure as we have proceeded in our previous lectures. Means what? First one is what? Find out the elemental stresses for each element. Here as there are 2 elements, means there are 3 nodes, 1, 2, 3. Means your global stiffness matrix will become of order 3 by 3. As there are 2 elements, find out 2 elemental stiffness matrices, means K1, K2. The next step is what? Find out or construct the global stiffness matrix K. You will get this K. The next step is what now? Find out the global force vector. Global force vector means to find out the global force vector due to the temperature effect as well as due to the point. Means first, third step is what? First, find out nodal force vector due to temperature effect. Okay. Then next, here second step is what? First step is what? Find out the nodal force vector due to temperature effect. Second step is what? Find out the nodal force vector due to point. Okay. These are the 2 steps. And next is what? Then finally construct global force vector. First find out the nodal force vector due to temperature effect. Due to temperature effect means Ft, and due to point means F. And finally construct the global force vector F. Okay, by adding Ft plus Ft and F. Okay, so in this way you will construct the global force vector. And the next step is what? Your fourth step is same, means construct the force and displacement relationship. And then finally apply the boundary conditions. Finally, by applying the boundary conditions, you will get eliminated equations, and by using these equations, you will get the displacement. Okay. So in this way, now we need to proceed in this way. So first step is what? Find out the elemental stiffness matrices K1 and K2. Okay. So here we will now determine the elemental stiffness matrices K1 and K2. Okay. So K1, elemental stiffness matrices. As we know that it is given by formula A1 E1 by L1 in bracket 1 minus 1 minus 1 1. Okay. So put the values. A1 is equal to 2400 into E1. E1 is equal to 0.7 into 10 to the power 5. All values are in mm square. Okay. Already this is in Newton per mm square. So write down 0.7 into 10 raised to the power 5 divided by L1. This is nothing but 300. 300 in bracket 1 minus 1 minus 1 1. So K1, you will get K1 as equal to 300 into 8. 8 times 2400. So 8 into 0.7. 8 into 0.7 means 56. 5.6 into 10 raised to power 5 into 1 minus 1 minus 1 1. Okay, so if we here if we multiply this 5.6 into 10 raised to power 2 into 10 raised to power 3, because we need to get this value as a common, 1 minus 1 minus 1 1, or you can get this, you can put 10 raised to power 5 as a common, but 10 raised to power 3, because the minimum value is 10 raised to power 3, as we should get this common 10 raised to power 3 in each your procedure. Okay, so K1 will become 560, 5.6 into 10 raised to power 6, 560 into 10 raised to power 3 into 1 minus 1 minus 1 1. And finally, if we multiply 560 to this matrix, you will get finally K1 as, so finally K1 is equal to 10 raised to power 3, it's common, 560 into 1 means 560 minus 560 minus 560 560. Okay, so in this way you will get first elementary stiffness matrix. Now next is what? K2. Find out the K2. So K2 will become E2 by L2 in bracket 1 minus 1 minus 1 1. So K2 will become equal to, E2 is what? 2 into 10 raised to power 5 into A2, 1200 divided by L2. L2 is what? 400. In bracket 1 minus 1 minus 1 1. Okay. K2 will become 400 into 3, 3 into 2, 6, 6 into 10 raised to power 2 into 10 raised to power 3. I am splitting this 10 raised to power 5 as 10 raised to power 2 into 10 raised to power 3, because we need to get this 10 raised to 3 as a common value, 1 minus 1 minus 1 1. So finally K2 will become, so this K2 will become equal to 600 into 10 raised to power 3 in bracket 1 minus 1 minus 1 1. Okay, to get this 10 raised to power 3 common, multiplying this 600 to this matrix, you will get K2 as 10 raised to power 3 as a common. Here we are taking 10 raised to power 3 as a common. 600 minus 600 minus 600 and 600. Okay, so this is the second element. First one is in between node 1 and 2, and second one is between node 2 and. Now construct the global stiffness matrix. Same procedure as we have discussed, or we have studied how to construct the global stiffness matrix. So global stiffness matrix K, it will become, as there are 3 nodes, so this K will become 10 raised to power 3, it is common value, 10 raised to power 3. Okay, so between 1, 2 and 3. 1, 2 and, so first place this elementary stiffness matrix over this box, then place this elementary stiffness matrix between node 2 and 3. Between node 2 and node, then you will get the global stiffness matrix. So if we place this first elementary stiffness matrix, then 10 raised to power 3 as a common, so 560 minus 560 minus 560 plus 560. Then second, 600 minus 600 between positions 2 and 3, 2 and 3. This is the box. Plus 600 minus 600 minus 600 plus 600. Remaining two values are 0. Okay. So in this way, you will get the global stiffness matrix K. So global stiffness matrix minus K will become K is equal to 10 raised to power 3 into 560 minus 560 0 minus 560. Now addition of this 11 0060 1160 means 1160 minus 600 0 minus 600 and plus 600. So in this way you will get the global stiffness matrix K as 560 minus 560 0 minus 560 1160 minus 600 0 minus 600 600. Okay, this is the global stiffness matrix. Okay, now next is what? So find out. Now we need, this is your global stiffness matrix. Up to global stiffness matrix we have discussed it. Okay, now next step is what? Next step is to find out global force vector due to temperature effect. Okay, so for first element we know that how to write down the nodal force vector due to temperature effect. Okay, so for first element this will become F1t F2t. It will become equal to minus E1 A1 alpha 1 delta t plus E1 A1 alpha 1 delta. Okay, so you will get the values as minus, now E1 A1, E1 is minus, E1 is equal to 0.7 into 10 raised to power 5 into A1, A1 is 2400 into alpha 1, alpha 1 is 22 into 10 raised to power minus 6 into 22 into 10 raised to power minus 6 into delta t. Delta t is equal to 30 into 30. Okay, this is the first value, minus E1 A1 alpha delta. As we know that this is the nodal force vector due to temperature effect. Okay, as we have derived this in our previous lecture. So you will get F1t F2t for first element minus E1 alpha 1 delta t plus E1 alpha 1 E1 A1 alpha 1 delta t. Okay, so in this way you will get same here, only here positive. 0.7 into 10 raised to power 5 into 2400 into 22 into 10 raised to power minus 6 into 30. So if we simplify this, you will get F1t F2t equal to minus, if we simplify this, you will get F1t and F2t as F1t is equal to minus 110880 and this is plus 110880. So this is the first nodal force vector due to temperature effect for first element. Okay, here we need to simplify this for second element. We need to find out the nodal force vector due to temperature effect. So for first, this value I will write this value here. F1t F2t is equal to minus 110 plus 110880. So this is your first nodal force vector due to temperature effect for first level. This is between equation 1 and now next find out the nodal force vector due to temperature effect for this second element. So for second element it will become F2T F3. The same procedure. Minus E2 A2 alpha 2 delta T plus E2 A2 alpha 2 delta T. Okay. By putting E2 A2 alpha 2 delta T all the values, or by simplifying this, you will get F2T and F3T as these values. Okay, here just calculate these values. Calci, you will get the answer as minus 86400 plus 86400. Okay. So for first element, this is the nodal force vector due to temperature effect. For second element, this is the nodal force vector due to temperature effect. Now we need to add these two nodal force vectors to get the force vector due to temperature effect only. Okay. So by adding these two values, we will get the nodal force vector due to temperature effect as F1T, F2T, F3T. Okay, just write down the positions of these two elemental nodal force vectors as. So for F1T and F2T, we know the values are minus 110880, minus 110880, plus 110880. For second and third equation, we know the values as minus 86400 plus 86400. This is minus. This is for second equation. 86400, and for third equation it is plus 86400. Okay, so in this way, just I am writing the positions of F1T, F2T and F3T for first and second element. For F1T and F2T, we know that for first element, these are the two values. For second element, these are the two values. Okay. So here, F2T, it will come two times. So write down these two values. 110880 minus 86440. So by subtracting this value from this, you will get finally the nodal force vector due to temperature effect as nodal force vector due to temperature effect as F1T, F2T, F3T is equal to minus 110880. So by subtracting this, you will get final as 24,480, and finally 86,400. Okay, so this is the final force vector, nodal force vector due to temperature effect. Okay. Now next is what? Find out the force vector due to point loss. Second is what? Due to point loads. Okay. Now due to point loads, find out the force vector. So due to point load, F1P, F2P and F3. These are the values for due to point load. Now from this diagram, first element, first node is fixed one. At this node, there must be some reactions. Okay. So at this node there must be some reactions. Similarly, at third node there must be some reaction R3. So for first node, point load is R1, for third node, point load is R3, means these are the reactions. And for second node, point load is given, and it is given equal to 400 kilonewton. So write down these point loads over the for this vector, nodal force vector. So first node, at first node there is reaction, there must be some reaction R1. At second node, force value is given 400 into 10 raised to the power 3 kilonewton, and for third node this is R. Okay. Now finally construct the global force vector due to this temperature effect and due to this point load. So to get these values, just add these two force vectors to get the final global force vector. So finally global force vector will become F1, F2, F3, okay, is nothing but F1t, F2t, F3t plus F1p, F2t, F3. Okay, this is simply the addition of a nodal force vector due to temperature effect and a nodal force vector due to point loads. Okay, you will get the final global force vector F1, F2 and F3. So if we add these two values, we will get finally force vector will become F1, F2, F3. This is nothing but plus, we need to add the force vector due to point load. This is nothing but R1, 400 into 10 raised to the power 3 and R. Finally, this will become F1, F2, F3. This is your global force vector. This will become minus 11080 plus R1. Now addition of this 24,480 will become equal to 44480. Okay, addition of this two values, this is equal to 480. So 424,480, and last one is 86400 plus R. Okay. Finally, you will get 400 into 10 means 1, 2, 4 lakh. 4 lakh plus 24,480. It is nothing but 4,24,480. So this is the final global force vector due to temperature effect as well as due to point. Okay. So up to this clear. Now next is what? Next is construct the force and displacement relationship. Then apply the boundary conditions. By applying the boundary conditions, you will get the elementary equations. By using these equations, you will get the displacement, and by using these displacements, you will get the remaining values, means stresses and reactions. Okay. So in this way, you can proceed. Just one new thing is what? Find out how to construct the global force vector due to temperature effect and due to point effect. Okay. This is the new thing in this example. Okay. So just try to solve the remaining portion of this example. Just try to get the displacement value U2 as well as the stress values as well as the reactions. If you are unable to solve these examples, or you are unable to solve this remaining portion, I will solve this example in your next lecture. Okay. So up to this clear here. In this lecture, just we have constructed our global force vector. Now in next lecture, we will solve the remaining part of this example. Okay. Thank you.